All right. This is one of those talks that got produced a long time ago, and then my agency created a situation where I couldn't present it, but I dug it up anyway because it does have some things that may be of interest to this audience. So move on to some things I'm sure you already know, but these are key to this presentation. First of all, we're going to talk about expansion factor, and that's just wait time plus run time divided by runtime. And if you think about it, it's a measure of user satisfaction or productivity. The lower, the better. The next thing is utilization, and there are a number of ways you can measure that. CPU hours used divided by CPU hours available, or you can base it on just the CPUs themselves. And it measures effective resource usage. And as I'm sure as you've observed, these two things are in a certain amount of tension. The folks who own the machine want U to be as big as possible, and the folks who use the machine want E to be as low as possible, but unfortunately, they tend to increase together. So this is what we're looking for. We want some sort of curve that relates expansion factor to utilization, and we can use this actually for both groups of people, the owners and the owners and the users, so that we can set expectations. That is, of course, both groups want what they want, and we need to tell them, well, you can't have that. And in some cases, you may be able to use this to conduct policy decisions and perhaps make things a little bit better. And one other comment, ideally, you'd probably like to operate your systems around the knee of that curve. That way things are not too bad for either group. Okay, do I get bonus points for mentioning your name? Okay, that's who I'm referring to.
I'm not that old, that must be a different person.
You and me both. These are some things that, again, I'm sure you already know about, but I always find them interesting. If you just take a naive first come, first serve or first come, first fit policy for your jobs, even a naive scheduling policy can get 40 to 60% utilization. Most of us are not satisfied with that. And if you add a more sophisticated dynamic backfilling, then you can get another 15% and maybe get up to 70% utilization without too much pain. If you want to take the step of reducing maximum allowable job size, you can do a little bit better. Of course, that just turns the big chunks into grains of sand, and you can pack things tighter. But I find this next quote from this paper real interesting. We made hundreds, perhaps thousands of small changes to hardware, software, and policy, yet utilization was affected little. And I think this was NASA Ames. So, in my opinion, achieving near 100% utilization while supporting a real workload, that's just unrealistic. And I guess we all know that. But that doesn't stop people from working on this. The effect of achieving very high utilization is a counterproductive decrease in the ability of the system to support the applications for which its acquisition was justified. That's a pompous way of saying if you make the owners happy, you're going to make the users unhappy. Okay. And also the replacement of many capacity jobs by any capability job, the ones, you bought a big machine to run big jobs, hopefully, then that's going to decrease utilization. So again, this is another example of the tension between expansion factor and utilization. So there are a couple of strategies that have been proposed, and users, you gotta love them. They tend to work around every strategy you come up with to defeat you. So if you give exact allocations, then what do users do? They hoard their allocation, and you end up with feasts and famines on your machine in terms of how it's used. So what do? You reallocate periodically, and then you're rewarded with multiple feasts and famines. Your other possibility is to over-allocate, and you can ask the airlines how that's worked out for them. In some cases, if things get bad enough, you'll drag the user off the machine, kicking and screaming, maybe. And one other thing you can do is try to focus on expansion factor and try to run at the knee of the curve, as I mentioned earlier. So what was the motivation for this study to try to predict one versus the other? Well, as I said, there are conflicting perspectives. High utilization is best since it justifies the high cost of a very expensive resource. There's the user perspective. They want lower expansion factor because it makes them more productive. But as you might expect, intuitively, expansion factor increases with utilization. Now, you can obviously you can create faux workloads where you can have 100% utilization and an expansion factor of 1, but those really just don't occur in real life. All your jobs are perfectly timed so that you have one following job that starts as soon as the previous one job ends, then life is good, but that just doesn't happen. So one question we are trying to answer here is to determine how much additional resource must be applied so as to decrease utilization and increase expansion factor. Now, what's the matter with that question? If you actually do this, if you actually deliberately decrease utilization, that is by limiting the workload, then you're going to make some of your users unhappy. Because they'll see, oh, well, you've got capacity you're not using, and all these other folks, you're rewarding them with low expansion factors, but you're giving me basically an infinite expansion factor because I don't get to use the machine at all. But in any case, again, we can use it to set expectations. So what's the process here? How do we actually go about doing this? Well, as you know, if you're going to do any kind of curve fit, you got to get data points, and we'd like to have a span of data points that have different utilizations and different expansion factors. Well, the problem right away is what? You can't manipulate your machine to change the utilization. It is what it is. And you can't rerun the same workload to get consistent experiments. So you've got a problem. But let's assume we can get the data. And based on this data distribution, we want to formulate some relationship with E as a function of utilization or utilization as a function of expansion factor. And we're going to use linear regression, which is just a pretty standard technique. So how do we obtain the data? Well, the actual data, as you might expect, if you've got 4 machines, you're going to get 4 data points. The utilization, as I said, is what it is, and the expansion factor over the time period of interest is what it is. And so with 4 machines, you'll get 4 data points. That's not going to give you very much interesting curve fitting opportunity. And it's not possible in practice to vary the utilization by fixing the workload and changing the number of cores. You can't just go out and change the number of cores on your machine at will. So what do? Well, you get a scheduler simulator. So we wrote one. We use actual job records as input. They're massaged a little bit to conform to the industry standard workload format. And this solves all 3 of the above problems. Okay, so what are this talk is not about the simulator, but let me just say a few words about what it can do. Input and output are both in standard workload format. There are a lot of utilities to evaluate this, so this conforms to that and allows us to easily analyze the output. It's got parameterized backfill, multiple queues, actually multiple queues implemented as one queue. And it can use actual or exact wall time estimates. And you can adjust that to find out what happens if users are more prophetic in their abilities than they normally are. You can use trial runs to mitigate job infant mortality. And individual job priorities are highly parameterized, so you can tinker with that too. Here are the input data characteristics. until you actually look at some of these data, you really can't believe what your users are up to. The number of jobs that we discovered that had 0 runtime is just amazing. We had some evil suspicions about what they were up to when they did this. Some of it is probably pilot error. We suspect some of it is deliberate activity that with evil intent, but we won't go there. And then there are multiple ways to measure your figure of merit. Over there, there's 3 different ways to measure expansion factor. We'll talk about that in a minute. So running these simulations, as it turns out, it's not feasible or even desirable to replicate every center's scheduling policy. At the time we had 5 centers, but they each have their own special sauce that they use to schedule jobs, and so we didn't want to push everybody into one mold, but we did want some sort of consistency across simulations. So basically, what the simulator did is it basically took the reciprocal of time since the start of the job log. If you think about that, that means the job that ran first is going to have the highest priority, the job that launched second is going to have the second highest priority, and so forth. So this is a way of enforcing the job launch order on the simulator. And also we turned on backfill to allow earlier than recorded runs. And the simulation runs, we varied the number of CPUs on each of the machines from 70% to 150% of the actual number of CPUs in 5% increments, so there were 17 simulation runs per machine. And it's important to note that when you run a simulator like this, it really does represent a viable or feasible job launch schedule. So this is not really, how can I say it? It's not a fairy tale. I mean, you could, if you had a machine that big, you could actually run these jobs in this order on that machine. Okay, so which expansion factor do you use? Well, you've got some choices. You've got the average expansion factor, and you can see how badly behaved that is. In this case, that means every job counts as much as every other job. Even if that job used only 1 core, its expansion factor was as valuable as a job that used thousands of cores. That probably doesn't have a lot of intuitive appeal. It didn't for us, so we didn't use it. The next one is the weighted average expansion factor. So you weight the jobs based on how many core hours they consume. And then finally, the one that is our favorite, or rather, I guess Larry Davis's favorite, is the 75th percentile expansion factor. What you do to get this is you rank order all your jobs by expansion factor, and then you start moving up the list as expansion factor increases until you get to the job that marks off 75% of your CPU hours used on the machine. And so that seems to be the one that's best behaved, and so we use that one for the curve fit opportunity. So here's the simulation results. The points in red are actual data. And of course, we made the simulations match as closely as possible to the actual data. And you'll notice there's a couple of machines there from my favorite site that seem to be not quite as well behaved. So we discarded the bottom 2 as outliers. The data's obviously not linear. Polynomial and logarithmic fits won't work. That's just Murphy's Law at work. And we need to enforce some sort of reasonable lower bound for which the utilization at which the expansion factor is 1. And ideally, we want a curve fit model that's invertible. That's fancy mathematical language that if I've got U as a function of F, it means I can back it out so that we get the reverse of it so that E is a function of U. So that's the first model. I won't explain it endlessly, but we ended up with, this is E as a function of U, and we've got about 27% relative error. as you can see from the data, that's pretty much unavoidable. There's no way you're going to fit that data exactly, but you can get pretty close. And then the second one is U as a function of expansion factor, and it worked even a little bit better. And you'll notice in both of these, we somewhat arbitrarily selected a utilization of 42% as being the point at which expansion factor would be 1, which in my mind is surprisingly low, but that's about what the data ended up being. And that's the results of the second model. And this is the comparison of the two. So if you, of the two models, U as a function of E and E as a function of U, so that worked out pretty well too. And as you can tell, at the bottom end of the curve, 42% is where you get the expansion factor of 1. Okay, so let me make just a couple of quick comments on this. To some extent, when you do simulations of this sort, in my mind, it's kind of like the dog walking on its hind legs. I'm sure you understand that. It's not that it's done well, it's that it's done it all. It's amazing. So, but again, in this study, every simulation run represents a feasible job schedule, assuming no downtime. And even accounting for downtime, the U versus E relationship is expected to be very similar. So we don't think that would be a source of uncertainty. And also the relationship can be used to estimate how much additional resource would have to be applied to lower the expansion factor for that workload. Now obviously, if you lower utilization, then users are going to attempt to fill the machine up again, so that's problematic. But some of the lessons we learned from this is, first of all, getting good input data is hard. There's even as nice as PBS job logs are, they can't, users will do things that you just can't figure out after the fact what was going on. Every good, even good input data will have idiosyncrasies. There will be a lot of jobs with 0 runtime, and that just really makes a mess for expansion factor. You have to do some things to kind of massage that data. And then scheduling policies will vary significantly, so that's an issue as well. So that's it.
Oh, thank you. Well, first, thank you. Questions? Yeah, okay. And I'll start.
So what did you, as a result of the simulation, what did you do? Did you make any changes to your scheduling policy? Did you decide to cap utilization at 42%?
No, this is something, this is a request that came down from the agency director. It was passed on to the deputy director, who passed it on to me, and I dutifully provided them with the curve that they could use to interpolate. And as near as I could tell, they finally decided that based on this information, they just didn't want to mess with it.
That's basically been my experience as well. So we track expansion factor, and we try to drive it to 1, because that's what our users want. And we
Sure.
get down to about 1.1, and everybody goes, that's pretty good.
Yeah.
Do you know what the expansion factor that you're targeting is? I mean, or that the centers tend to target in terms of what they're doing?
As it turns out, we have job classes. We have background, standard, high, and urgent. And there's a different target expansion factor for each job class. And it's like you're playing whack-a-mole. As soon as you satisfy one target, that satisfaction generally comes at the expense of another target. And we do have what we informally refer to as some of our gold card users. And we try to make sure that they are the happiest, or at least the least miserable. So.
So I really enjoy all the game theory that goes into this on both sides of the ball, right?
Yeah.
The user side, it's fantastic to get a user and to look at what they're doing and reach out to them and be like, you did a ace move, man, but I'm going to shut you down, just so you know. And then the management side as well, right? You have to show them, what are you getting, what are you putting money in for? So there's game theory there going on. It's fantastic from top to bottom. But what I've told Bill and others at Altair for a long time is we need to have a scheduler running on a quantum machine so I can tell the user, I don't know why you ran or didn't run. I can't tell you. There's no answer. It just is.
Well, we've discovered, too, that there's a third group of criminals involved in this, and that's the system administrators, because inadvertently, they got the impression that we were measuring site performance by expansion factor. And that was not the case, but that was their perception. And a lot of expansion factor is keyed off of the performance of large jobs, the one that use a lot of cores and run a long time. And so when one of these large jobs would come up at the queue that had waited a long time, what they would do is kill it off just before it launched, and then immediately re-queue it and relaunch it, knowing that the original version that got killed would never show up in the job history log as having run, and only the new version of it would show up, and it would have this miraculously low expansion factor. So, yeah. I mean, you gotta give them credit. I mean, there's.
Real quick, on the job mix, did you ever, I don't recall seeing it say what kind of job mix. You talked about breaking jobs up into smaller pieces, but were the job mix in this, like some jobs would take up to 20% of the system, others would take 50, or are you talking more, was there a certain threshold that you were looking at in this study?
No. On our machines, it's until recently, and we've taken some steps to mitigate that on some of our machines, but the time the study was done, it would be unlikely for a job larger than 1/4 of the system size to launch in a reasonable amount of time.
So all right.
That was kind of and to some extent that's still true, except for a machine that we've got that we've kind of keyed to run really large jobs.
Thanks. Time for maybe one more question if someone has one. Raise your hand. Okay, not seeing anything.
Okay.